So essentially, this is the rule for U substitution. It's a type of integration when you have a composition of functions. But this probably looks a lot like gobbledygook. So what I'd like to do is just roll you through a number of examples. So instead of remembering all of that crazy equation up there, here's what I want you to get. If you have a composition of functions, you want to find a way to rewrite it to make it much simpler. Find U for each of these. Each of these three examples has a composition, one function inside the other. Find U for each one. If you picked out the inside function for each of these, congratulations. Now next, I want you to actually take the derivative of each and then solve for dx. Here's what I mean. So, using that as your guide, find dx for each of the next two examples on your own. Well, that wasn't very smart of me. You can't find dx for the last one. You're actually solving for dt. So I guess that was an unintentional trick question. Sorry about that. Now, what we're going to do is we're going to plug u and dx or dt into each of these functions. That's right, way over on the right, I've taken this exact same equation, but everywhere I had 9x plus 5, I put in a u, and I substituted in for dx. So I'm rewriting each of these difficult equations, or integrals, I should say, and making them much more palatable. When you simplify, notice that any extra variables that might have still been around, any of the extra x's or t's that might have been lingering, will divide out every time. Isn't that nice? Now, taking the integral of something to the 27th or to the negative 1/2, or even just secant squared really is no problem. The whole point is to rewrite the difficult equations, use substitution to make them much easier. And, I should say, if you are interested, the answers might look like this. I didn't want to leave you without the final answers. And I also want to point out that once you integrate, sure, that's an easy integral to take. Don't forget to back substitute. If u was originally 9x plus 5, when you finish your problem, you should plug 9x plus 5 back into it, right there in the same spot. So each of these problems, make sure once you've integrated with u, take the time to re-substitute or back substitute so that you get your final answer in the same variable that it was originally written. Now here's a couple more examples. What I'd like you to do again is come up with u and dx, or in this case, d theta, possibly also. Find the substitutions you're going to use for both of these examples. I chose these examples because after the first few, as a matter of fact, several people are always wondering, hey, am I always going to get some kind of answer divided by a number? No, it always depends what your derivative is for that inside function. In this case, when we substitute things back in, we've got cosecant of u, cotangent of u times 4 du. Our value actually gets a little bit bigger. And by the way, if you happen to know what the integral of cosecant cotangent is, maybe you should remember the derivative of what equals negative cosecant cotangent. Anyhow, so in example 4, I just want to show you an example where this was not going to be du divided by a number. Sometimes it's multiplied. Don't forget to back substitute. For example 5, I put this one up because it is a little more subtle. Lots of people don't realize they need to do the chain rule here. They forget that the derivative of 1 minus x is actually negative 1, so they miss out on a negative sign. It takes a little fussing around, but by the time you actually plug in your u and dx and then rewrite it, you spend more time and effort rewriting the problem than you do integrating it. This integral should be really easy, just using the power rule. So the process is not too bad. Stay organized, write out these steps, and just be careful with the details. That's basically U substitution. Thanks.